Hello everyone, my name is Aditya Upasani. Along with my teammates Abhishek Vishwakarma, Yash Mahajan, Ryan D'Souza and our mentor Dr. Ranjan Balajain, I present QuantumPlayground, an interactive virtual lab platform for quantum computing. A quantum virtual lab like ours is needed because it brings otherwise inaccessible quantum experiments like Bell state analysis, GHZ and W state entanglement directly to students through an interactive, browser-based platform. Instead of requiring quantum hardware or local Qiskit setup, the lab allows learners to explore measurement in different bases, generate true quantum randomness, and all of the other experiments in a completely virtual, risk-free environment. By visualizing and interacting with these complex quantum phenomena, students can understand concepts that are impossible to grasp through theory alone, making the virtual lab an essential tool for modern quantum education. Using this website, learners can explore 14 experiments through a structured flow: theory, test, simulation, and certificate. Each experiment combines clear theory explanations, an integrated quiz to reinforce concepts, interactive simulations with configurable parameters, and auto-generated PDF reports that include circuit diagrams, figures, and derived metrics. Currently, we have 14 different experiments, namely measurement in different bases, Q random number generator, and multi-qubit superposition under quantum foundations, parity check with ancilla qubit and Q circuit identity verification under quantum logic and operations, Bell state analysis and noise effects, entanglement in 3 qubits GHZ state, and entanglement in 3 qubits W state under quantum entanglement and noise, BB84 quantum key distribution, superdense coding, and quantum teleportation under quantum communication protocols, tomography of quantum states under quantum state characterization, error detection with 3 qubit bit flip code, and error detection with 3 qubit phase flip code under quantum error correction. In this video, I will demonstrate 2 experiments from the platform. The first experiment we will look at is the BB84 quantum key distribution. It is an essential protocol for secure key distribution. Alice sends qubits prepared in random bases, Bob measures them in random bases, and they keep only the positions where their bases match. A subset is used to estimate the quantum bit error rate, that is QBER. If QBER is below the security threshold, the shared final key is accepted. This is the quiz for the BB84 quantum key distribution experiment. I will quickly solve the quiz right now. As you can see, we passed the quiz with a perfect score of 5 out of 5, which is reflected in the sidebar. Next, let's look at the lab simulation. The first step of this is the animated simulation tab, in which the user can check step-by-step animated BB84 protocol steps. On the left we have Alice, on the right we have Bob, and we can enable Eve right here with our desired interception rate. The user can click next step. The bit is transferred right in front of the user, and we can see the information such as Alice bits, Alice bases, intercepted yes or no. If it is intercepted, Eve bases and Eve result are displayed, and finally Bob bases, Bob result, and if bases match. The user can do this until the total number of bits defined. After all the steps are completed, the user can check the total number of bits, shifted bits, the QBER, and intercepted bits right here, along with their formulae. As the QBER is below 11%, that is the security threshold, no eavesdropping is detected. Hence, the shared key is generated. As you can see, when the QBER is above the security threshold, the shared key is not used as the channel may be insecure. Next, we will look at the protocol analysis section, in which we can run the entire protocol with just one button. Here we can set parameters such as number of bits, channel noise percent, that is the strength of the noise in the channel, as well as we can enable eavesdropping and its interception rate. After we run the protocol, the initial bits, shifted bits, final key length, and QBER are displayed. As the QBER is above 11%, the channel is insecure and there is possible eavesdropping. The BB84 protocol flow is given below, as well as the key comparison of the first 50 bits and the shared key. And finally, we will look at the performance analysis tab, in which we can vary a number of parameters like noise, number of bits, distance, number of eaves, and the fading factor. For this experiment, let's vary the number of eaves. We can set the number of trials per level, as well as the number of bits, channel noise percent, distance in kilometers. And here as we are varying the number of eaves, it is reflected in the parameter section. After the analysis is complete, it displays the lowest QBER, highest QBER, average key length, and average success rate. The user can view the QBER with different number of eaves in this chart, the final key length, as well as secure trials percentage. The user can also view the raw data in tabular format and can also download it in CSV format. That is it with the simulation. Finally, there's the certification page. After completing the theory and simulation, the user can generate a certificate as well as a lab report. This is the lab report that is generated. It has all the theory from before as well as key metrics and figures. The next experiment we will look at is parity check with ancilla qubit. In this, we can check if a particular binary string has even or odd parity using an ancilla qubit. This particular qubit is used to store intermediate computational results as well as perform measurement computations without disturbing the input qubits. I'll quickly give the quiz over here. Now let's look at the lab simulation. In this, the user can choose states for all 3 qubits. Next, we can view the circuit diagram used to generate this. And finally, the measurement outcome over here. As expected, there are even number of ones in this, so the measurement should be 0. That is even parity. The formula used to derive this is P is equal to Q0 XOR Q1 XOR Q2. Like the previous experiment, we can generate a certificate over here as well as a report. This is the report that is generated. It has all the ancilla qubit theory as well as the circuit diagrams, measurement results and other figures. In conclusion, QuantumPlayground offers 14 experiments with a unified learning path, interactive controls, and comprehensive auto-generated reports. It is ideal for classrooms, workshops, and demonstrations. Today I showcased 2 experiments, but the platform includes many more, from error correction and tomography to quantum randomness. Thank you for watching.